Beautiful. Okay, so let's talk about that last thermo assignment. And there's going to be a lot of questions on the test tomorrow on this. So I'm not sure everybody's kind of cool with this. So when you look at these pressure volume graphs, okay, there's certain things that you need to know. You're going to have pressure on this axis, you're going to have volume here. And so right away, that's going to be in newtons per square meter, and this is going to be in cubic meters. So there's 3 different types of processes you can have on these graphs. If you have a curved line like this, that's isothermal. So rather than an isothermal, what stays the same?
Temperature.
Yes. So this is going to be, your temperature is going to remain constant. Okay? So this is that first one that we worked through yesterday. This is the most complicated one in terms of how this plays out. So because of the fact that there's no change in temperature, okay, that change in temperature is going to equal 0. We're not saying there isn't a temperature. We're just saying that the temperature isn't going to change, okay? So delta U, and delta U is the sum total of all of the types of energies that you can have, okay? And again, this isn't the energy in the system, okay? This is the change in the energy of the system, okay? And again, there are no delta U probes. They don't exist. I'm not going to go, hey, just take a delta U probe, put it in the room, and you're going to get a reading, okay? It's an important concept, but true of many things in science, we can't measure it directly. So we have to infer what's going to happen. So delta U equals 2 things. It equals 3/2 NR delta T. And delta U also equals Q plus W, right? So right away, because Ryland said, oh, there's no change in temperature. So if there's no change in temperature, there's no change in delta U. Okay, so that means delta U is going to equal 0. I'm not saying we don't have energy in the system. I'm just saying the energy isn't changing, okay? That's all we're saying. So there's a couple of things that you need to have straight in your mind. One is the sign of work if the volume is getting bigger or if the volume is getting smaller, and understand how this plays out mathematically. So if the volume is getting bigger and an isothermal, what we call an isothermal expansion, okay, we would literally see this thing getting bigger. You would use work equals nRT times the natural log of volume, initial over volume, final, okay? So when the volume is getting bigger, okay, what's going to happen? No, it's final over initial. I'm sorry, I screwed that up. So when that volume is getting bigger, okay, then what's going to happen is that this work is going to work out to be, no pun intended, to be a negative value. It is a volume. Is it? Look on the back. Is it VI over F?
Yeah.
Okay, I had it right the first time. Then I started to second guess myself. I was like, I think that's right. No, I'm going to change it. So what's going to happen is that this is going to work out to be a negative value because your initial volume is less than your final volume. So that might be like 0.1, that may, like we talked about yesterday, that might be 0.5. So whenever you take, like this would be 0.1 over 0.5. So whenever you take the natural log of a value less than 1, that generates a negative value. So if the volume is getting bigger, this works out to be a negative value. So work is a negative value. There are certain things you just have to know. Volume gets bigger, work is negative. Now, how this plays out, if on a word description, it'll say work is being done by the system. So you gotta kind of understand the code of thermodynamic problems. So if work is done by the system, What that means is that this would be like me leaving all this money to Emma, and she's the system. She has to do work. Emma is the system. Work is going to be done by Emma, okay? That's going to cost her money. Work is going to be a negative value. So if you see work is done by the system, that means, another way to say that is that you are increasing the volume and it's getting bigger. So work done by the system and volume getting bigger means the same thing, okay? Because these particles have to push against what's trying to keep it in place, okay? So in either situation, volume is getting bigger, work is done by the system, that's going to be a negative value. So how this would play out, I'm going to tell you, hey, 500 joules of work is done by the system. What's the amount of energy that flows into it? Something like that. So what you have to be careful is, when I'm going to give you these numbers, I'm not going to explicitly tell you, hey, this is a negative value. You have to crack the code and go, oh, hey, 500 joules of work is done by the system. That means that's going to be a negative value. So in the problem, I will never give you negative values. You have to decide, hey, is that a positive or a negative value? Okay? That's going to be on you. Just because I give you a positive number doesn't mean that it's positive when you actually put it into the equations. Okay? So just be aware of that. Just be aware of that. Now, the other way that this can happen is that you could have a horizontal line. So if we have a horizontal line, what's staying constant? Pressure. So this would be isobaric. Okay? Now, this one, we're going to use work equals negative P delta V. This is a completely different equation from this one. So there's a couple of things that happen as you go across. Number one, the volume is getting bigger. Okay? So if you look at this equation, all this is saying, hey, it's the length and width of a rectangle, and we're going to make it a negative value. Okay, literally. It's the pressure is the height, the change in volume is the width. Okay, this is just nothing but the area of a rectangle. Okay, that's all it is. Don't flip out and go, oh, that's weird. It's a rectangle. Okay, the only thing that gets a little bit wonky is that we have that negative sign. Now, this is always going to be volume final minus volume initial. So if the final volume is bigger, which it is in this situation, and that's bigger than the initial volume, the delta, this is where it gets a little bit wonky. The delta V is going to be a positive value because you're subtracting a bigger volume from a smaller volume. But we put that negative sign out there so that way it's the same negative value like you get out of when you do the work calculation using NRT natural log. Okay? That's why we put that random negative sign out there so that way everything still works out to be the same thing. So if you look at these two equations and when you can use in each one. So I can't use work equals negative P delta V on an isothermal because the volume is changing and the pressure is changing. So I can't use work equals negative P on isothermal because everything's changing, nothing is constant. I can't use NRT natural log on an isobaric because the temperature is changing. So that's why I can't use that one. It's like, oh, okay, well, as I go across, I'm increasing the temperature. Well, then when I go to put it into this equation, I don't know which temperature to put in because the temperature was continuously changing. So that's why we have two different ways to calculate work. One is that NRT natural log, and if you need this equation isn't actually on your equation sheet because it's a real specific equation. If you actually need that equation on the test to do a calculation, I will give you that number, okay, or I'll give you that equation, okay? Don't memorize it. Do not waste time memorizing this equation. I will give that to you if you need it. Okay, So, as you go across, you're increasing the temperature. This one, the temperature stays the same. So let's go back to isothermal. On isothermal, delta T is going to equal 0. So what that means is that Q plus W have to add up to the same value. One has to be positive, one has to be negative. So if you look on that, for example, on question number 10, I say, okay, hey, you have an isothermal process. Can you figure out the amount of energy that's put into it? So if delta U is going to equal 0, that means Q plus W have to add up to equal to 0. But this is where you have to pay attention to the wordage and how that stays out. So, let me see if so on number, which one is it? 10. So this is the classic example. I say on number 10, on an isothermal process, 2.4 joules of work is done by an ideal gas, okay? So here's where you have to learn your prepositions. So that work is done by the gas. It's just like you guys. If you do work, raking leaves, whatever, that costs you energy and you feel tired. So on number 10, when you're told that work is done by the gas, that means that the volume is getting bigger. Okay, so that's why I said you have to understand what's the magic code. Okay, so work is done by the gas. That means the work value is a negative number. So what that means is the Q then has to be a positive number. Okay? So this is where you have to watch the signs. So here's typically where that particular question goes bad. Is that, oh, I know Q plus W has to add up to equal to 0. And you keep that work value as a positive number, and then you make the Q value negative. Okay? No, this is bad. I cannot emphasize this enough. I am never going to give you a negative value. You have to decide, hey, is this positive or is this negative? Okay? So pay attention to that. Now, if I had said that 2.4 times 10 to the third joules is done on the gas, meaning that we're going to compress it, then if work is done on the gas, that would be positive work because the volume would get smaller. Then Q would be a negative value. Okay? So that's why I'm telling you, when you get into the thermodynamic questions on this, pay attention to the sign. Now, when you talk about Q is kind of a one-trick pony. Either energy flows into the system or energy flows out of the system. Okay? There's no other way to sugarcoat that. If energy flows in, Q is a positive value. If energy flows out, Q is a negative value. Okay? That's pretty self-evident. Oh, energy is flowing in. It's a positive value. Things are going to warm up. Okay. So let's talk. So let me give you some hints on your answers to number 16. And by the way, if you want to hold on to this assignment and hand it in tomorrow, you can. So on number 16, that answer should be starting with the negative 8 and be something times 10 to the 5th.
Which one?
On 16A. Okay, so that should start with a negative number and be something times 10 to the 5th. On 16, that number should start with a 4 and be something times 10 to the 6th. Okay, so 16A, start with a negative 8, 10 to the 5th. That's just work equals negative P delta V. That's all that is. And then B is going to be 4 times 10 to the 6th. Now, on that graph on number 17, so let me give you an idea what that graph should look like. So you got your pressure, volume. So the first thing it says is that you're gonna do an isobaric compression, which means that we're gonna keep the pressure the same, but we're gonna make the volume smaller. So the first thing you're gonna do on 17 is just draw like a horizontal line like this, okay? So here's what's happening. Thought problems. Is the volume getting bigger or smaller? So is work being done on the system or by the system?
On the system.
So is work going to be a positive or a negative value?
Positive.
Positive value. So you should be able to look at a horizontal line on a graph and go, okay, here's a whole bunch of things that I know about this. Last question, Chloe. Is the temperature increasing or decreasing?
They're the same. Decreasing.
Which one?
Decreasing. Because the pressure is getting, the volume is getting smaller.
And the pressure is staying
The same.
the same. So this is the Danica analysis, okay, right? So you have PV equals nRT, all right? So Danica was a shining star yesterday with this equation. So as you go across, what's happening to the volume?
Getting smaller.
We're shrinking the volume. But what's happening to the pressure, Danica?
Increasing?
No,
Oh, it's decreasing.
No.
Oh, it's staying the same.
it's the same. It's a horizontal line, right? Okay, pressure staying the same.
Yeah.
So as the volume gets smaller, what has to happen to the temperature? It has to go,
Down.
down, right?
I don't know.
She's knocked out the last
Equation.
five minutes.
Yeah, it's like, oh, come on.
I don't know how
Okay.
to explain last night.
So just look at the equation, PV equals nRT. So the volume is getting smaller and everything is staying the same. The only way that can happen is temperature has to go down. So, since the temperature is dropping, Emma Hayes, is my delta T value gonna be a positive or negative value?
It's gonna be negative.
Yeah, because my final temperature is gonna be less than my initial temperature, right? So I'm gonna have a negative change in temperature. So, Rylan, if I have a negative change in temperature, and delta U equals 3/2 nR delta T, what's gonna be the sign of delta U?
Negative.
So now I'm gonna have a negative delta U. Now, here's the next question. This is where we're gonna fit all this together. Temperature is going down. We got that. Got it. Volume is shrinking. Volume is getting smaller. Work is being done on the system. Is work going to be a positive or negative number? As I go across, is work going to be a positive or a negative number?
Positive.
You're right, but you said that with absolutely no confidence. Okay? Why is work going to be a positive number?
The volume's getting smaller.
Yeah. So if you look at work equaling negative P delta V, right? So my final volume is going to be less than my initial volume. So that means I'm going to have a negative delta V multiplied by a negative pressure. My work's going to be a positive number. Work is being done on the system. It doesn't like it. This is why the other day when I pushed this down and that cotton caught on fire, because it went like, oh, this is bad. Okay, so we did work on the system and it increased that, like, okay? So work's gonna be a positive number. Okay? So what sign does Q have to have, Zach?
Negative.
Now, Q is gonna be a negative number. So is energy gonna flow into the system or out of the system, Zach?
Out of the system.
So here's what would happen. If I were to do this, physically, this is what you would see. I would take that syringe and I would put it into an ice bath, okay? Because I've got to get energy out of the system. And what you would see is that you would see this syringe move down because of the fact that it's pushing this thing down. The volume is getting smaller, okay? So I'm taking energy out of the system, and you would see this thing get smaller. Now, Zach, last question. Which one is the bigger number? The negative Q or the positive W?
Negative Q,
Why? You're right, but why are you right?
because changing U is negative.
Yeah. So that means this might be like negative 150, and that might be positive 100. Now, this won't work out well for Emma. So it's like, hey, Emma, I'm going to leave you $100, but my will says you have to spend 150 to make the world a better place. And she's going, well, that sucks. Okay? You left me 100. I got to spend 150. I'm going to be down $50 on this transaction. Well, this is fun. Okay?
Yeah.
But that's mathematically what's going to happen. Okay, so the next thing you're told on this particular problem is that now we're going to do an isothermal expansion, okay? It's isothermal. So all you have to do is take this line and bring it out like that. So that's all you have to have on number 17. Horizontal line with an arrow pointing left, because that's going to show that the volume is getting smaller with a constant pressure, and then an isothermal expansion is that we're going to bring it back to that point. Which one is going to have more work? The isothermal or the isobaric? Bethany? Yes. The isobaric or the isothermal?
Thermal. Isobaric.
Why? Which one's going to have more area underneath it? This one or that one? Yeah, because it's just a bigger area underneath it. Okay? There you go. Do not make that difficult. Do not make that difficult. Let's talk about number 9 to make sure that you have this right in terms of sign. So on number 9, you should, on like that first one, A and B, A should be positive, B should be negative. On C should be positive, D should be negative. That's the question about work. And on the volume, E is negative, F is positive. So if there's, again, if you're into flashcards, okay, you might make flashcards that says, hey, this is what happens when energy flows in, energy flows out. This is what happens when work is done by the system versus on the system and the change in volume. So again, if you're into flashcards, I'd make one that has something like number 9 on it. On number 8, that's where you got to go through this whole process. You should have a total of 5 different calculations. And then you're going to add them all together. So if all goes well on number 8, your answer should start with a 3 and be something times 10 to the 6th.
Yay.
Okay?
Looks like we got that one right.
So you've got to do total of 5 calculations. You got to warm the ice, melt the ice, warm the water, boil the water, and then warm the steam. By far and away, the biggest one, that most energy intensive process is the one where you boil the water. Okay, so boiling water is without doubt the most intensive, biggest part of energy consumption. So when you make macaroni and cheese and you boil water, that's going to take a lot of energy. Okay, just saying. That's going to take a lot of energy.
I'm gonna have
Your answer to number 5 should be around 90, and your answer to number 6 should be around 10. On number 1, so number 1's kind of a cool concept. I was literally eating an almond joy. So, first off, and if you need this conversion, I will give you this conversion, okay? Don't memorize it. So, you got the 230 calories. 1 food calorie is 4,186 joules, which is the amount of energy it takes to raise temperature of 1 kilogram of water. So on number one, what you're gonna do is find the total amount of energy if you were 25% efficient. So you take the 230 calories, multiply that by 4,186. That would be the total amount of energy you could use if you could use all of it. Okay, you can't. Your body doesn't use all of it. You only use about 25% of it. So you need to take that number and multiply that by 0.25. So that's going to get you about 200 or 2,400,000 and some odd thousand joules. Big number. Then you know, okay, hey, I'm going to lift this thing up, and if you look at the units, that's 980 joules per lift. Okay, so this is a total. This is why you pay attention to units. Okay, so the top number is how the total number of joules that you have. The bottom number is joules per lift. Well, the joules cancel out. The lift flips up. Hey, you get the total number of lifts that you can do. So that answer to 1A should be something times 10 to the fifth. Your answer to 1B should be around 250. Okay? So if taking 25% of that energy, then you can lift this thing about 250 times. Now, the coolest answer, I think, is question C, where it says if you take all of that energy and lift up a person that weighs 70 kilograms, how high could you lift it? So the answer to 1C is about 1,400 meters, which is about 1.4 kilometers, which is about a mile. So if you could take all of the energy in one candy ball, almond joy to be exact, and you could change all of that energy, all of it, pure energy, into lifting someone up in the air, you could lift them about a mile high. So, if you could use all of it. Okay, so I think I covered everything on that. One thing, your answer to 18A should be around negative 270 joules. That's where you've got to use that work equals NRT, natural log, VI over VF. Okay, so the answer to 18A should be around negative 270-ish. Actually, to be exact. Right. Okay? Are we good? Bethany?
On 5 and 6, it says that the joules are released, so would that mean that Q is negative?
Yeah, technically it would be because the temperature's going to go down. Yeah. But if you got a positive answer, I'm more concerned with the numeric value. Okay. All right. Are we good? Like I said, if you want to hold on to this assignment, you can. Danica was like, "Oh yeah, definitely hold on to that." Okay. So are we good? Last questions. Boom. Once, twice. Okay. So Danica, can you stop that camera for just a second? Because I got to move.